this is Angela Galloway, and we are working in STA220 now into Chapter 7. And so Chapter 7, if you're in the online class, is going to be our Unit 4. Unit 4 is Chapter 7 and 8. And in Chapter 7 and 8, we're going to start dealing with the normal distribution. And so if you're looking at the notes for Chapter 7, at the beginning we have a quick review. You probably won't need this if you are doing the online class. You probably have just finished this. This is more for my lecture students because it may have been a while, or we may have had a spring or fall break in between when we last talked about types of data. But what we just finished up in Chapter 6 was looking at discrete data, right? And so discrete data, we're thinking of a count. So we thought of number of successes for the binomial. We are now going to be getting into continuous data. Continuous data, if you remember, can be any point on a number line. So if we're just looking at the number line here, any point that I choose could be a possibility for a continuous data point. So we're thinking of things like height, weight, time, all those things could go anywhere on the number line. They don't just have to be a count. They don't have to be a whole number. They could have decimals, they can have fractions, whatever, right? So it can go anywhere on the number line. So that is the data we're going to mainly be dealing with for the rest of the semester. So here's some just examples of that, a little talk about probability. But moving on into Chapter 7, we're going to be talking about the normal probability distribution. So with discrete data, we mainly use the binomial distribution, but I told you that there are other distributions out there. We just don't have the time to go into them. But the binomial is discrete. The normal distribution is continuous data, and so there are also lots of other continuous distributions, but like I said, we're just going to have enough time to get to the normal distribution. The normal is the most common one, and you'll see that lots of data sets in real life happen to fall into this distribution or into this shape. And in Chapter 8, we're going to talk about why that's true for even more distributions once we start taking samples of our data sets. So here, these are the characteristics of a normal curve. So it's symmetric, it's unimodal, so it only has one peak there. It's centered at the mean, which means the mean and the median and the mode are all equal to each other. It's bell-shaped, which means it has those long tails, making it look somewhat like a bell. And that is because with those longer tails there, it's going to include any data that may happen to fall far away from the mean. So all of the data is somewhere under this curve, okay? And so what I was drawing here in my class is sometimes when students see this curve, they may think more of like a line graph or that there's points on this line, but this line is just describing what the histogram looks like. So for example, we would get our data, we would put it into a histogram. Down here we would have our observations, so whatever the x values are that we're collecting. Over here we're going to have our frequency, which is how many observations fell in each category, or the probability or the relative frequency, something over here. And then we're going to get these bars looking like this for a histogram, right? So this is showing most of the data fell into this middle section here at -2, and then we have some here at -3 and -1, all the way down, keep going down. So you've got this histogram, and you would lay that green line on top of the histogram. So that's just describing the shape of the data. That's not actually any data points on there. So just so you understand what that curve is showing us, it's just showing us the shape of the data so that we don't have to draw out the histogram every time. So the probability density function, we did that for the binomial. We had a PDF that we used, and we also used that in our calculator. The PDF for the normal distribution is this, a little more complex than the one for the binomial. And we really won't be using this very much. We're going to be using our calculator, but this is kind of just to let you know this is where it's getting its calculations from. So we can't forget the empirical rule. We're still going to be using the empirical rule here because the empirical rule is for symmetric bell-shaped distributions, and of course the normal distribution is that. So we can still use the empirical rule when possible. So here's some applications of the normal distribution, how you're going to use this in some of your homework problems. So Bowling Green's October high temperatures are approximately normally distributed with a mean of 71 and a standard deviation of 3. So this information tells us it's a normal distribution, so that lets us know that it looks like this. It's centered at 71 and it has a standard deviation of 3. Now, using what we know from the empirical rule, we can put our mean in the center, right, and then add and subtract our standard deviations to get an idea of where the data is falling, what ranges most of the data is falling within. So that's what I did down here. So I usually do this with all my problems in chapter 7 and moving on. You know, I draw out the curve, I put where the middle is, I may fill in all these numbers or just a few. And then when I go to my problem, I look at what it's asking and I reference back to this to see if I can get the answer just using the empirical rule. So the first question said, what percent of high temperatures, and this should say October. I told my class that I kind of changed back and forth which month I use on here, and I just didn't update that one. So we're talking about October. What percentage of high temperatures in October should be between 68 and 74 degrees? So we go down here and we see that 68 and 74 are both one standard deviation away from the mean, right? They're both 3 degrees away from 71. And so we know from the empirical rule that 68% of our data falls within one standard deviation of the mean. So our answer is just 68%. That's all we have to do for that one. How hot are the highest 2.5% of high temperatures in October expected to be? Well, that one we're still going to be able to use the empirical rule, but we have to do a little extra calculation. So if you notice 2.5%, how we're going to figure that out is we know that the empirical rule, 2 standard deviations away is 95%, right? So if we've got 95% from here to here, what's left over? Well, we have 100% of our data somewhere under the curve, right? So if I take 100 minus 95, I'm going to get 5, right? So I have 5% left over, and that 5% has to be distributed into both tails, okay? So because it's a symmetric distribution, whatever's on one side has to be on the other. So if I have 5% to distribute into these tails, I wouldn't put 4% here and 1% here, all right? Whatever I have on one side, I'm going to have the exact same on the other. So I need to divide this by 2, and that's how I get that 2.5% on both sides. So now, looking at that, once I've filled those in, the highest 2.5% of temperatures are going to be 77 degrees or more, right? So we don't really have an upper bound there. The upper bound would just be, you know, we can maybe look up what's the highest high temperature we ever had in October or something like that. But really, we just need to say it's 77 degrees or more. That's it, okay? Now, what percentage of temperatures are 67 degrees or less? Well, we go down here and we see 67 is not one of our numbers that fall exactly 1, 2, or 3 standard deviations away. So if that's the case, we can't use the empirical rule. So we need something else to help us figure out what is this blue area in here. And so what we're going to use for that is we're actually going to go back to this Z formula that we learned about at the end of chapter 3. We also called it the standard score formula. And so the Z formula, what it does is the reason why it's called the standard score formula is because we are going to standardize our observation and put it on this standard normal curve. So remember when we first did this z-score at the end of chapter 3, what we used it for was to compare distributions, right? So the example we did was we compared ACT scores to SAT scores. So we said that we couldn't just compare the scores on their own because they came from different distributions, right? They came from a different mean and standard deviation. But once we do the standard score, the z tells us how many standard deviations we are away from the mean. So if we figure out both observation z-scores, we were then able to compare that ACT and SAT score based on how many standard deviations away our observation fell from the mean. And that's what we're doing here. We're going to standardize our observation so that no matter what mean and standard deviation we have, we can use this z-score to then put it onto this standard normal curve. And the reason why that's going to be important is we have this normal table, okay? In the normal chart, this may look a little different than the one you have in your chart or in your book, but it's very similar to that. This normal chart is going to give us areas or probabilities for whatever z we're looking at on the curve, okay? This is all based on the standard normal distribution. So we have to standardize our observation first so that we can then go to the chart and find what that blue area or green area or whatever it is that we're looking for, okay? Now, if we didn't have that chart, or if you want to know how did they come up with these numbers, did they just magically know that if I'm at, let's look at like 3.0, if I'm at 3.0 that there's 0.0013 area to the left of that z. Well, no, of course there's got to be some mathematical formula behind it. And the formula behind it is the PDF that we talked about, this here. Now the way to find this, we're trying to find this blue area, is to find the area under the curve, right? If you've had calculus before, then you know that finding the area under the curve means we need to do the integral, right? We need to integrate it. If you haven't had calculus, then you have no idea what I'm talking about, and that's fine. But if you have, then you kind of understand that we would do the integral from negative infinity up to whatever area we want, or from A to B, etc. Okay, and we would calculate that. But that is a very difficult process to do, especially if you haven't had calculus, because then I'd have to go into a whole calculus lesson. So thankfully we don't have to do that. Somebody has already done that for us. They've already done that integral for all these possibilities, okay? The only thing we have to do is, to be able to use this chart, we have to convert our observation to a z-score, okay? So that's what we're going to do for these problems. So this normal chart here, you can get going to the formulas. If you want to print off the formulas that I said you can use for the final exam, this is one of those that's on there at the end where all the charts are. You can also go to in your chapter contents for your ebook at the bottom where it says appendix. The normal chart is in there as well. You can print this off, whatever. So you're probably going to want to have one of these sheets handy because it just makes it easier than having to go back and forth on your computer to the sheet, to try to find it. So it's just easier to have it printed out for you. Okay, so before we go back to the problem that we were working on, we're just going to do a few examples of how to use the normal table because it's very important, okay, to be able to read it correctly. And some of your homework problems are really going to look just like this, where you're just showing that you know how to read the table. So find the percentage of the data that would fall in the shaded areas below. So we're looking for this pink area here. Z equals negative 1.25. So notice that these have already been converted to Z values, so we can go straight to the normal chart. So Z equals negative 1.25. So I'm going to go over here. So see, we have negative 1.2 here, and 5 is here, 0.05. So this is the first decimal place, this is the second decimal place. So we're going to go down here, and this would be our answer, right? Because we're at negative 1.25. So 0.1056. And that's how we get that answer right there. This one, we're looking at 1.09. So if you go to 1.09 here, we're at 1.09 here, 0.8621. Now notice that I've already written the answers in here. We didn't put 0.8621 as the pink area here. So why was that not the pink area? Well, look at the chart. You can always look at the top of your chart, and that's going to tell you what the chart is giving you, okay, what area the chart is giving you. So you notice that the shaded in area is the area to the left of the Z, okay? So our chart will always give us the area to the left of the Z. In this example, we wanted the area to the right. So we looked up in the chart and we got this 0.8621, but we want this pink area. So we can use the complement rule, right? If it's not over here, then it's over here. So they're opposites, so we can subtract from 1. So we can do 1 minus 0.8621, and we get this area is 0.1379. Okay? So sometimes you can just look at the chart and get the answer. Other times you need to subtract from 1 when you look at that answer. If you're looking for that area to the right, you're going to have to subtract from 1. You might also have a situation like this where we're trying to find an area between 2 points. In that case, we need to look up both points in the chart, and then we can subtract these values to get what's left over in the middle. Okay, so we would look up negative 1.8. So negative 1.8 would just go right here, 0.0359. We get that there. Then 0.64. We go to 0.64 right here. We get 0.7389. Okay, and so we have this is all the area there. This is just this little tail. We need to subtract that part off, and we get 0.7030, and that would be the area right in here. Okay, so those are kind of the 3 ways you could be asked about using the normal table. So now that we've kind of learned how to do that, let's go back to this, this question that said what percentage of temperatures are 67 degrees or less? Okay, so it's over here. So what we want to do is calculate our z-score. So we're going to do 67 as our observation, 71 and 3 are the mean and the standard deviation that were given to us in our problem. We get negative 1.333, so that means that our observation is 1.3 standard deviations below the mean, right? So let's look that up in our chart. Negative 1.33, so negative 1.33 here is 0.0918. That's what we got there. That will be a percentage of 9.18%, right? So we would expect about 9.18% of days in October to have highs that are 67 degrees or less. All right, now what about 79 degrees or more? So again, 79 does not fall exactly 1, 2, or 3 standard deviations away. So we're going to plug this into the Z formula. We get 2.67. Look that up in the chart, and you should get 0.9962. Now that's not the area to the right. That's the area to the left. Because 79 is above the mean, right? So you're definitely not going to have 99% of your data above 79, right? That doesn't make sense. So we need to subtract from 1 there, and we get this number 0.0038. So a very small amount of the data is above 79 degrees. So we would say that would be unusual if we had a high temperature in October of 79 degrees or more, right? Because it's only going to happen less than 1% of the time, 0.38% of the time. It's not impossible, but it's unusual. Here we're showing how to find in between 2 temperatures, okay? So you can look at that later if you need to. The last thing we might have to find is, for the ones we've been doing so far, we had the observation and we were trying to find the percentage. We could also have the percentage and want to find the observation. For example, if we wanted to know the coldest 5% of October days, they gave us a percentage, and we want to find the z-score that relates to that percentage, okay? So in that case, we're kind of using the chart backwards, okay? So we have the area is 0.05, so this area to the left is 0.05. Now another thing I have to mention though is how they're going to write it, okay? Z alpha is one of the ways that we notate, especially some things we're going to get into in some later chapters in chapter 9 and 10. But Z alpha, alpha is always our area to the right. Now that can be a little confusing because our chart, the normal chart, gives the area to the left, okay? But alpha is always the area to the right. Our chart just happens to give area to the left. There are other normal charts out there that give area in the middle and to the right, to the left. You know, there's all different normal charts. Ours for the book just happens to be to the left, which I think is fine to use. It's less confusing than some other charts I've seen, but just always remember alpha is the area to the right. So if we want to know the coldest 5% of October days, that would actually be notated as Z sub 0.95 because that's the 95% above that. Okay, 5% is below, 95 is above. So if I was to look this up, I would look up the 0.05 in my chart. Now I'm going to look it up differently. This time I'm looking for 0.05 in the middle here because now I actually have the area and I'm trying to find the Z that it relates to. Okay, so I want to look for something close to 0.05. And you can see that I've already got these circled in here that I did from my class. So you would look for something close to 0.05. And so you would notice all of these are getting close, close, and now we're getting, you know, farther away from 0.05. So it would be in between these two numbers here. So usually on your homework, they'll allow you to do any of those answers, either negative 1.64, negative 1.65, or even do something in the middle like negative 1.645, something like that. Either of those answers, any of those answers would be okay. So I put all three there, any of those answers, but of course you'll just put one into your answer. Then the warmest 10% of days, that would mean the upper 10%, so Z sub 0.10, but we're going to look up the lower 0.9. So we'd look that up in the chart and you should get a 1.28. So how we're going to use that is we could answer a question like this. What range would the highest 15% of high temperatures in October fall into? Okay, so the highest 15%, we're looking for this blue area over here to be 0.15. Okay, that's going to be our alpha. But in our chart, remember, we always look up the area to the left. So if we have 0.15 over here, we subtract that from 1 and we get 0.85 to the left. So let's go back to our chart and see what 0.85 corresponds to. Let me go over here and erase some of these so you can kind of see a little better. Okay. So we're looking for 0.85. All right, so you see in here, these two, you're always going to find two numbers. Well, not always. Sometimes you'll actually get something exactly on the number that you want, which is great. But usually you're going to find that one number is a little higher, one's a little lower than what you want. Just choose the one that's the closest. So 0.85 is closest to this, 0.8508, right? It's also close to the 0.8485, but it is closer to this one than that one, right? So we're going to go with this. And so we see the Z that that corresponds to is 1.04. So that's the Z we're going to use. So we're going to use a Z of 1.04. Okay, so that is our Z value. But we want to know what the actual temperature is, right? Not just the Z value. So now we need to figure out, well, what's the observation that corresponds to a Z of 1.04? And so the way we do that is, in this chapter, really the only formula we have is this Z formula, the Z equals X minus mu over sigma. So in the chapter, we're going to use the normal chart and the Z formula in some combination, okay? We're also going to talk about doing it on our calculator, but even when we're doing it on our calculator, that's what the calculator's doing. It's using the Z formula and the normal chart, okay? So we've got 1.04 is our Z, right? We just figured that out. We've got mu and sigma, which came from our original problem, 71 and 3. X is the only thing we don't have. So we can solve this equation, right? We would do 1.04 times 3. Then we would add the 71, and that gives us X equals 74.12. So the highest 15% of high temperatures in October are 74.12 or more. So this page is pretty important because this shows how we're going to do all this stuff on our calculator. Okay, so let me get back to my calculator here. So I'm sure you're going to like this part. Some of these problems, unlike uh, earlier in the semester when we were doing like standard deviations, some of those are definitely much more too time consuming to do by hand. Okay, some of these I honestly don't think are that bad to do by hand, because you use the z-score, you look up in the normal chart, not really a big deal. However, some students just like using the calculator instead. So I would say whatever you feel most comfortable with, go with that. If you like using the calculator for everything, go for it. If you'd rather do it by hand, do that, or do it both ways for a while, and then to kind of just double check your answer, and then you can decide on which way you like the best. So what we're going to be using is the normal CDF and the inverse norm. Okay, those are the two commands that we're using in this chapter 7, and then we'll also be using it going forward. So we're looking at this same example we've been working with. I'm just going to go through and show you how we would do all these on the calculator. Okay, what percentage of October high temperatures are 67 degrees or less? We're going to go to distributions, the same place we went for our binomial PDF and CDF back in chapter 6. We're going to do the normal CDF. Okay, um, the way we put in our information here is we do normal CDF, lower bound, upper bound, mu, and sigma. Okay, so what that's talking about is we've got, this isn't going to be a very great drawing, but just pretend it looks good. So our mean is 71, right? We're wanting to know 67 degrees or less. So we're wanting to know this area over here. Now remember when I told you what we're really doing is we're finding this area under the curve, right? So when we're finding area under the curve, we have to give a range. We have to tell it where we want to integrate, where we want to take the integral. So we're going from the lower bound to the upper bound. So the lowest part of the range to the upper part of the range. Then the mean and the standard deviation come from the population that we're dealing with, okay? So looking at this, what is our lowest value here? Now you might say, well, I guess it's 0. Well, is it 0? I mean, could a temperature be less than 0? Well, yeah, it could, right? So do we know what the lowest possible temperature is? Well, not really, right? I mean, we could probably look back and figure out in Bowling Green what was the lowest high temperature in October that we ever had. That would probably give us a lower bound. But really, our lower bound in this case is negative infinity, right? Because we don't know what it is. It just goes out forever, for all we know. So negative infinity is what we'd like to put in here. But our calculator does not have an infinity button. So I'm just going to make something up that's a very, very negative number, okay? And so I use this negative 9999 number, okay? Now it doesn't really, you don't have to use that number. If you look at some YouTube videos or something else on how to use the normal CDF, you might see instructors use different numbers there. There's nothing special about this number. I'm just trying to make something really negative to put in place of a negative infinity. Okay, so this is what we're going to use for infinity and negative infinity, the negative 9999 or a positive 999. The upper bound, though, we do know, right? It's going to go from negative infinity up to what? 67, right? So 67 is going to be our upper bound. Our mean is 71, and our standard deviation is 3. So that's all given in our problem there. And then we do enter. And you see we get 0.0912, which is about the same thing that we got when we did this using the z-score and our chart. Now this calculator answer is actually going to be the exact answer. The normal chart is rounded somewhat because the z-scores only go to 2 decimal places. So since we're always rounding those, our probabilities are going to be rounded as well. So if you're doing it both ways and you notice that your answer on here is a little different from what you did by hand, don't worry too much. As long as it's approximately the same, you know, within a hundredth or a thousandth of each other, then you shouldn't worry too much about it. And the homework is gonna, it's pretty lenient on these, that it's gonna accept kind of a range of answers, because some students are doing this on their calculator, some are doing it by hand, some are doing it with calculus, so there's a lot of different answers that could be there, but they're all gonna be pretty close to each other. Okay, the next one says, what percentage of October high days would we expect to have a high temperature of 79 or more? So now we are going to go, our lower bound here is going to be 79, right? We're going from 79 up to infinity. So if we're doing a lower tail area like this, our lower bound is going to be negative infinity. If we're doing an upper tail like this one here with 79, then the lower bound is going to be that number, 79. The upper tail is going to be infinity, okay? And then we have 71 and 3 again. And we get 0.0038. Now C, part C, this one will really save you time using the calculator, okay? When we did this one by hand, going from 70 to 75, you would have to calculate the z-score for both observations, look them both up in the chart, and then subtract the probability. So this is going to be much quicker to do it this way. So we're looking for 71 is our mean. We're going from 70 to 75. Okay, so we're looking for this area in between. Sorry, that's not very pretty there, but just pretend. Use your imagination. I draw much better on the actual board. Okay, so when we do this, we're going to do normal CDF again. So second bars, that distribution area, normal CDF. We're actually not going to use the normal PDF at all. I know for the binomial, we use the PDF and the CDF, but we don't use the PDF at all. We're just using the CDF. So our lower bound is 70, right? We're going from 70 to 75. So 70, comma, 75, comma, 71 for the mean, 3 for the standard deviation. I'm going to get 0.5393. That's what we got there. The highest 15%. So part D, this is also going to be much easier when you do this by hand, okay? I'm sorry. Doing it on the calculator is going to be much easier than doing it by hand. So we're looking for the highest 15%. Right, so this was what we were looking for. So in our calculator, second distribution, number 3 is inverse norm. So we use the inverse norm when we're doing basically the inverse of what we did in A, B, and C, okay? So when we're given the percentage and want to find the observation, we're going to use the inverse norm, okay? So this, we're going to put this in like this here, inverse norm. We put the area to the left, the mean, and the standard deviation. So what is our area to the left here? We want to find the upper 15%. So the area to the left is going to be 0.85, right? So we're going to put in 0.85. So you're always going to put it in as a decimal, not as the percentage. Put it in as a decimal. 0.85, the mean is 71, and the standard deviation is 3. And you get that, 74.11, right? And so that is the point here, and then it's 74.11 or more, right? It's that area over there. So that one definitely saves you time if you use that instead of doing it by hand. So I definitely like using the inverse norm on the calculator. Okay, then we have a few more examples to go through how to use the normal CDF and the inverse norm, just some other situations. 7.3 is about assessing normality. Now, normally, what we would do to assess normality is this is more of a real life application. So, in your homework problems, usually they're going to say, here's your data and this is a normal distribution. So you know you can use the normal distribution. In real life, you're not going to be given that, right? Somebody's not just going to say, here's some data and it's normal. You know, you're going to have to figure out, is it normal or not? So usually how we can figure that out is by putting it in a histogram, right? If we put it in a histogram, we're hopefully going to see a shape that looks like this, right? Like this up here. We're going to see that curve happen, that it's symmetric, bell-shaped, the mean and the median are equal, etc. Okay, and so that's great. We can use the normal distribution. The problem is if you have a smaller data set, sometimes that histogram won't always look normal when in reality your data might be normal. Okay, so in that case, we have to use something else to be able to tell if we have normal data or not. And so that what we can use is we can use these normal probability plots. Okay, and so I'm not going to talk too much about what all this stuff is here, but I'm just going to show you that you can get normal probability plots off of statistical packages like SAS or SPSS. I think probably even Excel does it, but our calculator does it as well. And so it can be just a quick way to put in your data and figure out if it looks normal or not. So how do we know if something is normal or not using these normal probability plots? What we're looking for is we're looking for an approximately linear relationship. So this here, let me erase this so you can kind of see the original there. There we go. So you can notice here that this looks more like a curve, right? It starts to have this curvature in there. That would be not normal. This, however, of course there's a little bit of up and down movement, but it's basically a linear pattern, okay? And so that's what we're looking for in these normal probability plots. So how do we do this in our calculator? When we go to stat plot, which is where we went for scatter plots or box plots, the very last one is a normal plot. Okay, so you want to put in your data. We could put this data into our list. So go to stat, edit, put it in list 1 or whatever list you want to put it in. In this example, I happen to have mine in list 4, so that's why this says L4. But you go there, pick that normal plot, and then it's going to give you this output. Remember, if you don't see it correctly, go to the zoom stat. So go to stat or go to zoom and then zoom stat, which is usually number 9. Okay, when I look at this, I would say that looks linear, and so I would say I can use the normal distribution, okay? And so once I know that, then I can go ahead and use the z-chart, the normal CDF, use the inverse norm, all that, the empirical rule, whatever I need to answer my questions because I know that my data comes from a normal distribution. Okay, so the normal distribution is a very important distribution for you to understand. Like I said, we're going to be using that for the rest of the chapters. So 8, 9, and 10 are all going to reference back to chapter 7. So chapter 7 is a very important chapter to understand and to understand how to use the normal CDF and the inverse norm on your calculator, how to read the normal probability chart. If you have any questions about that, please let me know so I can try to clear it up for you as soon as possible so that you don't continue on into the later chapters still kind of confused about these more basic concepts before we get into some of the harder ones. All right, so that's the end of chapter 7. Just let me know if you have any questions and I'll try to help you out. All right, thanks.